or actually a shell. Hollow inside. Infinitesimally thin edge. It is centered at 0, 0, 0. And let's go ahead and establish some coordinate system. So X to the right, Y up, Z coming out at you, right-handed coordinate system. And I have a charge sitting right there at the point 0, L, 0. And I want to figure out the charge, oh, and this right here has a surface charge density uniform surface charge density of sigma. And so that would be equal to the total charge on the sphere, we'll call it Q sub S, divided by the area. And what's the area of the sphere?
Pi.
What's the volume of the sphere?
4/3 pi r cubed.
Yep, take the derivative of that with respect to R. Do you want to do it in your head, Mo?
4 pi r squared.
There we go, 4 pi R squared. Where R is the radius of the sphere. There's a more generalized math which goes into that, but the circumference is the derivative of the area of a circle, and for a sphere, the surface area is the derivative of the volume. All right, I have some Q up here. And what I want to know is, what is the force on Q? Not Q sub S, but Q. And we're going to go through the exact same process. We're going to start out with a differential. I'm not going to do a differential of just a single point, but I'm going to do a differential of a ring. So I'm going to look at a ring running along here. And look at the force coming from this ring. And then integrate. So if we sort of expand that, I've got my ring here. I got the center here. I know this distance here is big R. This distance here is some value of Y. And then I have this point up here where this distance is L. That distance is little r. I seem to have put these in some bizarre order. What can go wrong? We'll do it off of memory. All right. So the charge on this ring right here is something we'll call dqs. It's infinitesimally thin. So all I need to do is figure out the area of that rim. Well, I'm looking at the circumference here. First off, what's the circumference of a circle? What's the area of a circle?
Pi r squared.
And what's the derivative of that with respect to r?
2 pi r.
There we go. So our circumference of that ring right there is 2 pi times fancy R. So let's go ahead and call that fancy R. I can figure out fancy R in terms of big R and Y, because I've got a right triangle right there. So big R squared is equal to Y squared plus fancy R squared. Or fancy R is big R squared minus Y squared to the 1/2. I know that any point on this ring is going to be, so this point on the ring is going to put a force in that direction, but I will always have another point on the opposite side of that circle pointing in the opposite direction, horizontally speaking. So the only thing that will remain is the vertical component. So we end up with the force on Q, the electric force on Q. Set up the standard I hat, J hat, is equal to K sub E Q dQs over R squared times, let's see, I need to define something else here, so I'm going to make this angle here theta, and I'm going to make this angle here alpha. And I want just the vertical piece, so that would be cosine alpha J hat. Questions on how I got that? Oh, technically that should be a D. It's a differential still. All right, so I have alpha, which is is a variable, little r is a variable, dqs, that's my differential. Big Q and Ke are constants, and J hat's a constant, so those will get pulled out, but I got 3 variables here, so I need to get it in terms of a single variable. So force, electric force on Q, I guess there is a direction there, yeah, is equal to J hat, K sub E Q, integral cosine alpha over R squared dQs. So I started down that path and then veered off of it. So we need to get dQs in terms of, well, Y. Uniform density over there, so sigma is equal to dQs dA. dQs is equal to sigma times the differential of that area of that ring. Circumference I know, basically if I took that ring and I snipped it and laid it out, it's just a giant rectangle, a really skinny rectangle. So this is equal to sigma times my circumference, which is 2 pi R squared minus Y squared to the 1/2, times the thickness of this ribbon. So I have this ring that I need to figure out the thickness there. Well, if that angle there is theta, d theta would be this. I need to expand that. So I have this ribbon, this circle that's going around this would be the thickness of it. That distance there is r. This angle here is d theta. What would be that length? Flashback to trig.
Sine d theta.
No. It's not a right triangle.
Would be the law of cosines. Whatever that would be.
Well, that's a really complicated way of doing it. Actually, I haven't used law of cosines. I imagine we would get there eventually. This is part of a circle. So if I have part, because again, it's a circle in any direction you go in. We're dealing with part of a circle here. And I want to relate the angle, d theta, with the radius of that circle and the arc length.
Is it S over R?
Say it again.
S over R are going over the radius?
All right, so the angle is the arc length over the radius. Therefore, what is this arc length here? That's the relationship I wanted. So,
Oh, R times theta then?
which in our case is d theta. So times r d theta. So I now have dq in terms of y and theta. Well, at least I got rid of the q, even though I've introduced another variable here. So we got j hat, case of eq, integral of cosine alpha over r squared. Cosine over r squared times sigma 2 pi r squared minus y squared to the 1/2 r d theta. It's just all, it's like it's opening up like a beautiful flower. All right, let's pull the constants out front that we can. Big R is a constant, that's the radius of the sphere. So we have this force, electric force on Q, J hat, K sub E, big Q, big R, sigma 2 pi. And what we're left with still is cosine alpha, R squared, big R squared minus Y squared to the 1/2. And I've already pulled the R out, d theta. And now, questions? All right, Patrick said it before, that's our next step. Law of cosines. We're looking at the triangle. That's big R, that's little r. This is L, this angle here is theta, and this angle here is alpha. I need to get little r in terms of theta. I need to figure out what cosine alpha is. So let's do law of cosines where we have a cosine alpha. Flashback to what the law of cosines is. Now that you flash back, if I want to find cosine of alpha, I'm dealing with the side opposite, so I got r squared equals Chris, you look like you're about to say something.
No, I'm not sure.
Okay.
Are we doing the Pythagorean theorem?
Law of cosines is Pythagorean theorem when it's not a right triangle. But Pythagorean theorem should be in there. If alpha is equal to 90 degrees, we get Pythagorean theorem. So let's start out pretending this Pythagorean theorem. So r squared would be equal to, if that's the hypotenuse, little r squared. So that's how log cosines begins, minus, and this is the factor for if alpha is not 90 degrees, the two variables that I have right there, so 2RL, and then the cosine of the angle opposite that side mentioned here. So the opposite of R is alpha, cosine alpha. Law of cosines. So we can solve for cosine alpha. And that's going to be equal to r squared plus little r squared plus L squared minus big R squared over 2RL. So we now have everything in terms of R. All right, next. We got that d theta there we gotta deal with. Well, we figure out the theta bit there. We got theta here. Let's do law of cosines again. We got little r squared equals. And the reason I'm starting with little r squared is because that's the side opposite theta, which is I need to do something with because I got a theta right there.
Big R squared minus L squared.
Plus L squared.
Minus 2 big R L cosine theta.
All right. Now I want to get to d theta, so I have to do a derivative here. So let's do a derivative. R is a variable, so this is 2 little r dr. Big R squared is a constant, L squared is a constant, and so then minus 2RL, the derivative of cosine is negative sine, sine theta, d theta. And so I'm left with d theta is equal to 2's cancel out. Little r, big R, L. Actually, I want to keep the sine theta there. D R, D little r. I feel like I'm about to take the long route around. Oh, no. Good there. That's good. Use. Yeah, good there. Good there. Nope, so far so good. Cosine alpha, I have Oh, okay. I haven't, there's nothing wrong here, I just took an extra step I didn't have to. The extra step is this piece right here. So what we're gonna do is we're gonna get it in terms of R, little r, instead of y. That's the difference. If I'm looking at this triangle here, or I guess this triangle here, this radius is just gonna be little r sine of alpha. So that's gonna be little r sine of alpha. So we are now left with that whole mess right there, which I'm just gonna call, whatever, I'm not using, M. Just because I don't feel like writing it. So the electric force on Q is equal to this vector M, which points upwards, times the integral of cosine alpha, so r squared plus L squared minus big R squared over 2 RL R squared R sine alpha d theta. I've got the sine theta there. And then sorry, let me just take a moment here.